W1VLF. Hey everybody, my name is Paul, W1VLF. Welcome back to the lab. Today we're going to talk about notch filters for the AM broadcast band. If you're like me, you enjoy listening to the AM broadcast band. Unfortunately, I have a 610 kilohertz transmitter that is less than a mile away from me, and it produces an incredible signal. Plus, excuse me, 70 over S9, and that's just tears up all the receivers. So I could build a high-pass filter, which you've seen me do in the past. I did a video on that, and that works really well. But that negates the rest of the AM broadcast band, and I still enjoy listening to it. I could pad it down by 30 dB or so, get it into the range of the receivers, but then unfortunately then all the rest of the signals are padded down. So what we're going to talk today about is a notch filter. And it really is just a very simple device. It's just a parallel resonant circuit that you put in the coax line. And I don't know if you can see this very well, but I'll have some much better pictures for you to look at in a minute. This is an old loop stick. Remember the AM loop sticks you used to hear about? And a couple of silver mica capacitors. Just a parallel resonant circuit in on one BNC, through the parallel resonant circuit, and out on the other. And this is something I just threw together, and it works. It works pretty well, but it's not really designed with high performance in mind. It has a pretty deep notch, but it also has some pretty wide shoulders, so most of your adjacent channels are kind of gone or down quite a bit. And I'll show you that too on the network analyzer over there afterwards. This is exactly the same thing. BNC in and out. This is my little test board, and these two clips here just hold devices that I want to test and put in series with the network analyzer. So over here you have a coil, and then the capacitors in parallel, and that's it. I'll see if I can pop this off. Yeah, and again, you'll have pictures of these, but this is just, what's it look like? 3/4 of an inch long of number 61 ferrite rod. If everybody's got to have an old AM receiver antenna laying around somewhere in their box of junk, and that's what this is. And I just cut it off and sanded the end down, and I glued it to a stainless steel bolt. I glued a nut to the ferrite, and then just screwed this in. And then I threaded this PVC so that it would act as an adjustment. So essentially, I made my own loop stick, because although I have hundreds of loop sticks, I don't have one that I know has number 61 ferrite rod, and that I also know it has the right amount of turns to give me the right inductance. So I'll give you some close-up shots of this. Let me see what else. So this is not going to be a do this exactly and here's how you build it. It's going to give you an idea of what you need. A couple of pieces of PVC pipe, some silver mica capacitors. And by the way, you want to use silver mica capacitors. The Q on these capacitors is astronomical, and it really kind of helps with getting the shoulders of this notch circuit to be very sharp, or much sharper than if you used any other kind. In this one, kind of a design thing here. This one has a lot of inductance in the inductor and not much capacitance. So here I used 2.8, 2800 picofarads of capacitance and only like 20 microhenries, which means that in order for it to be resonant, that's a different ratio. Normally an antenna rod made for the AM broadcast band maybe has 250 microhenries. This only has 24. So most of it is coming from the capacitors, which are the higher Q element. And that's what accounts for the much better performance. You could put, like I said, you could do a high pass filter, but and that works really well. unfortunately, you end up with not being able to see any of the broadcast band, and that I didn't want to have happen. So I'm going to show you the concepts behind how this works, how I arrived at these components, and a calculator that you can go online and calculate your own for your own frequency. By the way, this little coil here is 10 microhenries or so, maybe 12 microhenries without the core in place, and I think 24 with it. And this stainless steel bolt. And again, remember, it has to be stainless. If you put regular iron or steel in there, it's going to mess things up. The Q, anything magnetic. So I guess let's see what else. Anything else? I guess that's it. I'll zoom in and kind of show you this a little bit better here in person, and then we'll go over and look at the graphs, and then we're going to go over to the SDR. Today we're going to be using console 3, and we're going to be using a on loan RSP-DX. And I gotta admit, the RSP-DX with its built-in notch filter works really well. Not notch filter. It's built-in broadcast band notch filter. It works really well. Unfortunately, all your broadcast band is gone. So if you have one big offender like I do, it's like right out that window, which you can't see. This will give us on the neighborhood of 30 dB of attenuation. So they're running a kilowatt. They have maybe some gain, but anyway, 10 dB down would be 100 watts. 20 dB down would be 1 watt. And so this makes it look like it's running about a 100 milliwatt transmitter. And you won't believe how effective it is. So, all right, I won't ramble anymore. I'm just going to zoom in and show you these pieces sort of in real time. I'll call them out, and then we'll go over and look at some of the graphs, and then we'll go over to the RSP-DX and see the real world, how this really works. All right, let me set up. Okay, I'm back, as I like to say. Okay, so here is it's one of them little Pomona boxes. I already had a BNC on it. I threw it in there, made it resonate, and just because that's what I had. Oh, there's a loop stick. I'll try that one, and the right capacitor in parallel. And to adjust this one, it's a standard loop stick, so you just turn the screw here, and it works okay. You know, if you were only interested in, say, my frequency that I need to delete is on 610, and the ones if you were only interested in 1,000 and above, you know, 1 megahertz and above, this would work. This would be fantastic. But this is really a much better way to go. Here I have 3 961% microcapacitors, all junk box stuff. I picked this stuff up at flea markets, and you never know when you're going to need it. So I'll pop this off. Here's the coil. So this is all not glued together. It takes a little retuning every time you take the cover on and off, because you're dipping the coil, the ferrite into the coil more or less. So you just have to be a little bit careful about that until you're done. And once you seal everything and get it all nice and compact, then you just make the adjustment and lock it down with this this lock nut here. So that comes out. Here's just the inductor, and the inductor is 35 turns of this Litz wire. But what's really important is not so much the real size of this coil, but that you end up with about 10 microhenries, 10 to 12. I'll give you the exact values later. And this is just another one of those end caps that's glued down to the board so that I could test it for you here. So you just plug that in, plug that in. This BNC here, this one is the in, this one's the out. Really doesn't matter, it's symmetrical. But so you can see coming in, you have a parallel tuned circuit. That's it. So let's go look at some of the stuff on the computer and show you some of the graphs and some closer up pictures and whatnot. And then we'll go from there. Look at this. I got to figure out a way how to show this stuff without having this in the way. Oh well, if you can laugh. Okay, so this first slide shows the two notch filters being compared. the black trace number 1 with the marker at the top of the screen that says 610 kilohertz and something like, I can't really read that, it's too small, in the 50 dB down range. But you can look and see that it does not come out of its notch for, up to a couple of megahertz or so. This sweep is out to 20 megahertz, so you could get an idea that once the notch goes away, it's still a flat passband all the way up, so you're not going to see any attenuation anywhere else. Also, the red is about 31 dB down, and you'll see that the 30 dB is plenty. The benefit of this one is look how narrow the notch is, and look at the 6 or 8 or 10 dB, 12 dB of adjacent channel that you're not losing due to the low Q of the other system. So again, this goes out to 20 megahertz from 10 kilohertz to 20 megahertz. This is the sweep response. The next slide that you see will be close up, so you can get a really good look at what happens to these notches up here when you design one properly. All right, so now what we're looking at is a sort of a close-up expanded view, 10 kilohertz up to 2 megahertz, so just above the AM broadcast band. And if you look at that black trace, which is the old prototype, you can see that there is places where it's 10, 15, and almost 20 dB down in the adjacent channels. And look how nice and sharp and narrow and how fast it returns to being a flat response. You'll see this when how effective this is when we go to tune it. Anyway, just wanted to show you that close-up view, and now I'll go to the last slide is going to be one that is just for, it goes out to 30 megahertz because they thought, geez, I made the first slide at only 20. Maybe people are interested all the way up to 10 meters with the single antenna. So that's what we're going to do on that one. Okay, not a whole bunch more to see here. Basically, just wanted to show you that the band pass or the through pass of this filter out to at least 30 megahertz is essentially nothing. So I won't dwell on this, but you can see the 2 notches over here, and out to 30 megahertz, it's very flat. Real quick, just to show you that the coil itself without the ferrite core inserted is 12.4 microhenries. I'm going to just show each one of the components here. This slide shows the value of the inductor when it was tuned to 610 kilohertz. So right at 24 microhenries. You can see, and that's variable all the way from 12 to probably 40 microhenries, but all I really need for this is the 24.2. Okay, well, looks like I blew it. I threw away or deleted the picture of the capacitance meter. So, but it's 2828 pico and 20 picofarads. So instead, I think I'll just leave a few seconds of each one of these close-up shots up here, and then we're going to move on to. All right, so let's look at the resonant frequency calculator that we use to determine the types of values that we're going to need. So we're going to type in resonant. Whoop, it's already in there. So let's grab that. I'm not sure the mouse is going to show up exactly. I have 2 screens here, and the mouse, it doesn't seem to be showing up in exactly the right area. So, but I'll have to figure that out later. Just follow along. Resonant frequency calculator, the second one down, works really well. And if you look at what we have here, here's the circuit I was telling you about, just a coil and a capacitor in parallel. Very, very, very basic. So let's add in the values that we saw on our test meter. So let's see, we were around 24, not 254, 24.2 microhenries, so that's okay. And here we are at 2820 picofarads. That's micro, so we're going to go down to pico, and then we're going to hit calculate. And this number here, the number down below in red, should come up at around 610, and it did. Okay, so, and it shows the values down here in the circuit diagram, 24.2 and 2820. That resonates at 610. So the coil you're going to wind is really around 12 microhenries, but by introducing the core, the piece of number 61 ferrite on that threaded screw, you're able to lower or increase the inductance from 12 up to 24 microhenries. So there's an alternative way to do this. I don't know, let's say you had a, 3,000 picofarad capacitor. So we'll just type in 3,000. Okay. And we'll say 30 microhenries, just to show you that you can use this calculator in the other direction. So whatever 30,000 PF and 30 microhenries equals is going to show up down below here. So if I hit calculate, it's going to come out to resonate at 530. The highest Q element in this circuit is the capacitors, the silver micas. So you want to make sure that you don't go, because you could go in the other direction. You could say, oh, I have 300 picofarads and let's see. And I want to be on 610 kilohertz and do the calculate. And now it's going to tell you need 220 microhenries, which is like typical of an AM broadcast ferrite core antenna you'd find on the back of an old stereo or something. Unfortunately, the coil is the lowest Q in the circuit. So, and the Q equates to sharp shoulders, as you'll see. So we want to minimize that. So if we wanted to tune to, let's see, where are we? 610. We're going to go with 24 microhenries again, and 2800 or so. Get rid of that 610 in there, and then ask it to recalculate. And yeah, 613. I didn't put the exact values in, but anyway, so that's how that works. It's a great calculator. Let's just see the page here. Wonderful for doing this kind of work. But if you're designing something, go heavy on the silver mica capacitors here and light on the inductance. All right, on to the next part of the video. Okay, guys, W1VLF back. We're at the Ham Shack computer now. Excuse me, and we're tuned to the 610 kilohertz signal that I talked to you about up here. Got it muted because it sounds horrible, but if you look over here, you're going to see that there's a S9 plus 71. Now, granted, I'm running a big dipole. It's a 160 meter dipole. And I've played around, let me go back to home, with RF gain and IF gain here, AGC on and off. And I can't seem to come up with a combination that will allow me to hear adjacent stations. So let's just take a look at this. I'm going to turn the filter on, the notch filter. This is the RSP DX. And this is a ton better than the previous filter. So let's just see what it does. You can see I'm tuned to the 610, which is 70 over. Again, it's a kilowatt, like right outside my door, just about. So here we go. We're going to turn that on, and it drops it from 70 to 20, so about 40 dB. And most of, let's see here, crank this up a little bit. And we'll narrow it up. Most of the AM broadcast band, or actually all of the AM broadcast band, is gone. Okay, there's maybe a few tiny little carriers in here, blah, blah, blah. I'm not sure exactly what these are, but 610 is still 30 over S9. Now, again, I can change the RF gain, but I've got it set to default. And I have this set to, with the AGC on, off, on. It's much better with the AGC on, if I turn it on. All right, so there it's on. And again, I'm going to shut the filter off so we can, filter's now on. I'm going to turn it off. Okay, you can see the 610 is back up to 70 over. And there's all sorts of products being generated here. But let's go up into the in the memory section here. Go to number 2, and we're going to go in the middle of 75 meters. And we'll squeeze it up a little bit so we can see a little bit more of 75 meters. Let's see, someone here talking. Let's see here, pop this. It looks like there's somebody right here. I'm going to put in the filter. So let me bring back to go to home, and here we go. All right, so let's tune somebody. Tune a sideband station right here.
Couldn't ask for anything more fun to use.
Just works great. So I'll get a clip of you on
all
here.
All right, and I'm going to turn
Rick,
the
and,
internal notch
your
off.
Transmission. We'll get a little more audio and.
It's essentially just blown away because that signal is so big. Maybe with a much smaller antenna system, you would be able to run this, but with that notch filter out, turn it back on again.
Dynamic mic, the dynamic
brings
mic,
75 meters back up again.
SM58 sounds real
okay.
Good too.
So very, very impressed with how well that filter works. So let's go back to memories. First memory bank. We're going to go to 610. And we're going to squeeze it up. We're up at plus 71. Now, before when you saw me take the ferrite rod out of pulling that little cap off the top, that's how I'm going to sort of disable the filter. So I'm not going to detune it every single time, but I'm pulling that ferrite bar out, that little cap I had. So I'm going to drop it back in there and adjust it for minimum. Okay, so we went from 71 to 38. So what's that, about 33 dB of attenuation? We'll go up to 60 now. This is New York City, 190 miles away.
The question is, what makes you keep going back? Well, it's experience. That's exactly that experience that separates Mercedes-Benz of Edison from everybody
610.
else. It's called the Ray-Catino way.
Go up to, well, I think 720 here. Or 680, 710. Okay, I'm going to pull that core out, so essentially the filter is coming out of the circuit. Okay, it's just not able to cope with that. Put the core back in, and of course I got to readjust it again. If you look over here, you can see me readjusting it. Okay. Oh boy, I hope I'm gonna get nailed by the police, by the YouTube police. Okay, this is 90 miles away. This one's 90 miles away. 640 is another. It's a little too close. Let's go up to 1710. There's a station up there that's, or 1700.
Between 45 and 50.
And I'm going to pull that out. Again, here we go.
48 to 53.
Okay, so it makes the whole band unusable. Or makes it usable, depending on how you want to look at it. So let's go back to the home plate here. And we'll turn on the notch, which again, oops. Oh, that's because I have the filter in. Let me take my filter out. Okay. And now I'm going to put in that one. We're up at the very edge of the band, so the filter's starting to roll away a little bit. Let me squeeze this up a little bit. You can see down below here, but the filter's starting to come back out again. You know, we're starting to get back into where 75 meters. I mean, where 160 is. Let me just drop my, let's take that out. And we'll just drop in that one. So basically, with this filter, with this notch in place, you can go anywhere you want in the broadcast band, plus or minus, a bunch of kilohertz from that big 610. So let's go up to 75 meters with this notches off. Let's go up to 75 memories. That's number 2. I think somewhere around here. Let's see if everybody's talking here. No, here's somebody right here. Here, this is my notch filter. Put it back to.
It's very odd to have it up that early. I mean, the minute you sent that text.
So I'm going to pull my notch out.
So that's why I said, hey.
Now this is only notching that one station, right? Because this is the one big offender in my life.
Doing out there, like pulling cable out to my garage.
And you can see all the harmonic energy, all the distortion products, every 10 kilohertz. 320, 330, 340, 350. And I'll drop that back in again.
Yep. Somebody coming in. And,
so it really is a quite a useful way to be able to still use all the others. If you have one big station that's giving you a lot of problems, that's the way you want to go, is with a notch filter. So let's go back down to the AM broadcast band again, 610.
They are told when it comes to coronavirus.
Yeah, see, and I didn't have it tuned
dictator
completely
of the
either.
worst kind.
There we go.
But it gets worse.
I'm turning the
Biden's
screw
coronavirus
right now.
advisors are even worse than Fauci. They want to shut the nation down 100%.
Look at that. Here, watch.
And have the government
90 miles away, right next to a 1 kilowatt, 50 kilohertz away.
If you think that's bad.
Unbelievable. So anyway, any questions or anything that would, give you a comment? By the way, I'm up to 902 subscribers, and I'm really trying to get to 1,000. So if you know anybody who's interested in this kind of stuff, please share it with them. Let me shut that off. You don't want to hear that. If you know anybody who's interested in this sort of stuff, please share it with them, or perhaps my high pass filter video. I'm finally getting into a position now where I can make some more, so that's what I'll be doing. Again, please subscribe, and also I have an Instagram under W1VLF, which I'm experimenting with, just sort of showing things that show up that are much easier to put up there than do a whole video. Thanks again. Press the subscribe button and the notification bell. This is W1VLF signing off from the W1VLF Ham Radio Shack computer. 73.